Welcome to Pastor Victor's Academy. Embark on a journey through the world of engineering mathematics and electrical engineering with our educational tutorials designed specifically for engineering students. Whether you're mastering calculus, solving complex circuit problems, or exploring power systems, Pastor Victor's Academy is your ultimate learning companion. Join us as we break down complex concepts into clear, easy-to-understand lessons, helping you build the foundational knowledge and skills needed to excel in engineering mathematics and electrical engineering courses. Subscribe now to kickstart your learning journey and gain the confidence to tackle engineering challenges head-on. Let's unlock the world of mathematics and electrical engineering together, one lesson at a time.
Welcome to Pastor Victor's Academy. It's nice having you here again. I believe you've watched my previous videos. Thank you so much for watching, liking, sharing, and subscribing. So in this lesson, I'll be talking about types of function, composition of functions, and the inverse of a function. Please pay attention as we go on. There are different types of function, and the first one is the constant function. It is a function that assigns the same value to all the values in the function's domain. Now, if we say that f of x is equal to 3, what this means is that for every value of x, f of x, which is the same thing as y, will be 3. So let's begin to plot. We'll have, when x is equal to 1, we'll have 3. When x is equal to 2, we'll have 3. When x is equal to 3, we'll have 3. When x is equal to 4, we'll have 3. You can see that if we do the same for values in between 0 and 1, 1 and 2, 2 and 3, 3 and 4, we'll be having a straight line running from here to infinity. Then depending on where we started from. So that means from negative infinity to positive infinity, that's negative infinity, positive infinity. The value of the function is the same, which gives birth to a horizontal line. So in other words, we can say that any function that gives us a horizontal line when plotted on a graph is a constant function. Okay, the second one is the identity function. It is a function that returns the input value as the output value. In other words, the output value of the function is the same input value of the function. Here we have the equation y is equal to x, or f of x is equal to x. So if x is equal to 1, that means f of x is equal to 1. So that is what the identity function is. Identity function of x is equal to x. ID of x is equal to x. When we plot the graph, you see that it's a straight line that passes through the origin. So let's go ahead and plot the graph. When x is equal to 1, y is equal to 1. When x is equal to 2, y is equal to 2. When x is equal to 3, y is equal to 3 of 1. When x is 0, y is 0. You can see that it's a straight line that passes through the origin. So that's what the identity function is all about. The next function I want to talk about is the linear function. The linear function has the equation f of x is equal to mx plus c. Now where m represents the slope, x is the input variable, and c is a constant. So is the intercept of the graph. It's called a linear function because every time you plot this graph, it will give you a straight line, though not a horizontal line, but it will give you a straight line. The straight line will only pass through the origin if c is equal to 0. But if c is not equal to 0, that means the straight line will cut y, where y is equal to c. So that's what this function is about. Take for instance, we have f of x is equal to 2x plus 2, or let's say 2x plus 5. We want to plot the graph, and we'll have 1, 2, 3, 4. Then we'll have, let's say 2, 4, 6, 8, minus 2, minus 4, minus 6, minus 8. Now, when x is 0, we'll be having 2 times 0 plus 5. That will be 5. So f of x, these are f of x, and these are x. So f of x is equal to 5 when x is 0, and that's this point. When x is 1, we'll be having 2 times 1, that's 2 plus 5, we'll be having 7. So we'll have this somewhere here. When x is minus 1, we'll be having 2 times minus 1, minus 2. Minus 2 plus 5, that will be giving us 3. So at minus 1, we'll have 3. When x is minus 2, we're having 2 times minus 2, that will be minus 4. Minus 4 plus 5, that will be 1. So at 1, we're having minus 2. So when we connect all the points, we'll be having a straight line that cuts the y-axis at 5, which is the intercept. It cuts the y-axis at 5, and that gives us the intercept. To know where it will cut the x-axis, that means at that point f of x is equal to 0. So we'll be having 0 equal to 2x plus 5, which implies that minus 5 is equal to 2x. X is equal to minus 5 over 2. So this graph will cut the x-axis at minus 5 over 2, and that is equal to minus 2.5. You can see this is minus 2, this is minus 3. Here should be minus 2.5. The next function I want to talk about is the signum function. The signum function is a function that has a specific value at certain points in the domain. Now, here's the definition. Now, the signum function is equal to 1 when x is greater than 0. The signum function is equal to 0 when x is equal to 0. And the signum function is equal to minus 1 when x is less than 0. Let's plot the graph. For values greater than 0, that means 0 point something. So let's take, for instance, from 1, we'll have this, we'll have this, we'll have this. When x is less than 0, minus 1. So that means around here, when x is minus 1, we're having minus 1, minus 1, minus 1. Then when x is equal to 0, signal function is 0. That should be at this point. So how do we draw the line? Looking at this equation, you can see that the signal function is equal to 1 when x is greater than 0, but not equal to 1 when x is equal to 0. So in that case, we'll use a bracket here, a normal bracket here. Then we'll draw a line that extends to infinity. Then the same thing applies to here. Signal function is equal to minus 1 when x is less than 0. So we'll also use a normal bracket here. Then we'll draw a line that extends to infinity. So this is what the signal function looks like. The next one I want to talk about is the Heaviside function. The Heaviside function is just like the signal function. It's just a little difference. That's the definition for it. Now we have h of x is equal to 1, 0, x greater than 0, and x less than or equal to 0. So what this means is that when x is greater than 0, that means 1, 2, 3, 4, whatever, as long as it's greater than 0, the Heaviside function is equal to 1. But when x is less than or equal to 0, the Heaviside function is equal to 0. So what do we have? If we want to plot it on a graph, we'll have 1 here, then here is our 0, 1, 2, 3, 4. When x is greater than 0, that means for this point, the Heaviside function is equal to 1. Then when x is less than or equal to 0, Heaviside function is equal to 0. So we are having this. So if we want to draw the line, we'll just be having this extending to infinity. Then because Heaviside function is not equal to 1 and 0, we'll use a normal bracket. Then for this part, since at 0 we have 0 and going towards negative infinity, we'll use a square bracket for here and draw a line that extends to negative infinity. The next one is the modulus or absolute value function. Mod x is equal to absolute value of x, which is equal to x0 minus x greater than 0, x equal to 0, and x less than 0. So what does this mean? It means that when x is greater than 0, that means the value of this function will be the value of x. In other words, we'll be having the graph of an identity function when x is greater than 0. Then when x is equal to 0, we'll also be having 0 as the output value. Then when x is less than 0, what do we have? Negative of x. The essence of this negative is to make the value become positive. Now take for instance, x is minus 1. Take the negative of minus 1, you'll be having 1. X is minus 2. Take the negative of minus 2, you'll be having what? 2. So that's what this part means. That once x is a negative value, then the result will be the negative of x. And that makes that answer, or that value rather, become positive. Let's plot the graph. Now, for x greater than 0, that's this part of the graph, the modulus of x is equal to x. In that case, when x is 1, modulus of x is 1. When x is 2, modulus of x is 2. When x is 3, modulus of x is 3. When x is 0, modulus of x is 0, meaning that we'll have this. When x is less than 0, modulus of x is negative of x. In other words, taking the negative of x. So at minus 1, we'll be having 1, minus 2, 2, minus 3, 3. So absolute value of minus 1 is 1. Absolute value of minus 2 is 2. So this is what our graph looks like. You can see when x is greater than 0, we'll have identity function. Then when x is less than 0, we'll have the inverse. Before we go ahead, there are 3 properties of the modulus function I want to talk about. The first one is that modulus of x is always greater than or equal to 0. This implies that the modulus of x can never be a negative number. The second one is that modulus of negative x is the same thing as modulus of x, which is always greater than or equal to 0. And the third one is that modulus of x plus y is less than or equal to modulus of x plus modulus of y. Now, what this implies is that the modulus of the sum of x and y will always be less than or equal to the modulus of x plus the modulus of y. Take, for instance, we'll have a number 2, then we'll have a number 5. Let's also have negative 2 and negative 5. So one assume that x is 2 and y is 5. So we're having that modulus of 2 plus 5 is equal to modulus of 2 plus modulus of 5. That's modulus of 7 equal to modulus of 2 plus modulus of 5. That's 7 is equal to 7. Okay, now let's assume that x is equal to minus 2. So we'll be having modulus of minus 2 plus 5, and that will be less than or equal to modulus of minus 2 plus modulus of 5. 5 minus 2, that gives us 3. So modulus of 3 less than or equal to modulus of 2 plus modulus of 5. And we'll be having 3 less than or equal to 2 plus 5. 3 less than or equal to 7. So it's clear that this is lesser than this. So we're having 3 less than 7. It's not equal to 7. Instead, it's less than. Let us assume that y is minus 5. We have a modulus of minus 2 minus 5 less than or equal to modulus of minus 2 plus modulus of minus 5. This gives us modulus of minus 7 less than or equal to modulus of 2 plus modulus of 5. This gives us modulus of 7 less than or equal to modulus of 2 plus modulus of 5. 7 less than or equal to 2 plus 5. This implies that 7 is less than or equal to 7. You can see 7 is equal to 7. So modulus of x plus y will either be less than or equal to modulus of x plus modulus of y. It cannot be greater than 8. Let's look at the next type of function. The next type of function is the greatest integer function. So this is how the function is represented. It is defined as the largest integer less than or equal to x. The largest integer less than or equal to x. 1.5 is equal to 1. Now, the greatest integer function of 1.5 is equal to 1. It is not 2. Remember, we are talking about integers. So it is not 2. We define it as the largest integer less than or equal to x. So it's not 2 because 2 is greater than x. These are x, these are x, these are x. 2 is greater than x. It is 1 because 1 is the only integer that is close to 1.5 and less than 1.5. The same thing applies to this. If the greatest integer function of 1 is equal to 1, this is already an integer. We said less than or equal to, so in this case it is equal to, because 1 is the largest integer, which is equal to 1 as the input value. Then in this case, the greatest integer function of minus 2.1 is minus 3. Remember that minus 3 is lesser than minus 2.1. It is not minus 2 because minus 2 is greater than minus 2.1 when you begin to move across the number line. So it is minus 3. You will count minus 3 before counting minus 2.1. Let's plot the graph and see what the graph looks like. So this is the graph of the greatest integer function. You can see that for values of x between 0 and 1, the function is equal to 0. For values of x between 1 and 2, the function is equal to 1. For values of x between 2 and 3, the function is equal to 2. So we have a square bracket here, whereas we have a normal bracket here, showing that at x equal to 1, the function is equal to 1, not 0. So you can still have a square bracket here, indicating that at x equal to 1, the function is equal to 1. But at x equal to 1, the function is not equal to 0. Instead, the value is very close to 1, but not 1. So the moment we get to 1, then the function becomes 1. Then we keep going like that until we are very close to 2. But the moment we get to 2, the function becomes 2. We keep going until we are very close to 3. The moment we get to 3, the function becomes 3. The same thing happens this side. You can see we are moving from -1 towards 0, -2 towards -1, -3 towards -2. So for values between -2 and -1, the function is equal to -2. Remember that -1 is greater than -2. Then for values between -1 and 0, the function is equal to -1 because 0 is greater than -1. So as we move very close to 0, we'll be having -1 as our answer. But the moment we get to 0, our function becomes 0. So that's what the greatest integer function is about. We'll be talking about the next type of function, which is the polynomial function. This is the equation of the polynomial function. P of x is equal to an x to the power n, an minus 1, x to the power n minus 1. Then we keep going down till we get to a2 x to the power 2, a1 x to the power 1, a0 x to the power 0. So whereas this is the input variable, then these ones are coefficients. They are just coefficients. The essence of n minus 1 is just to show that this is different from this, this is different from this, this is different from this. So they are just the constants standing beside the powers of x. So we'll call them coefficients of x. Now n represents the degree of the function. So for first degree, we'll be having 1, second degree, we'll be having 2. We keep going like that to whatever degree we have in mind. Then the shape of the function depends on n and the coefficients. So we cannot say that this particular graph is the graph for polynomial functions. It just depends on the degree of the polynomial, that's n, and the constants, that's the coefficients. So we can plot a particular graph to represent all the polynomial functions. We'll have different shapes for the polynomial function. So other functions I want to talk about before we go to the next thing, the rational function. So this function is simply the ratio of two functions, a of x divided by b of x, where b of x is not equal to 0. So each time we have a function as a numerator and another function as a denominator, definitely that's a rational function, but the denominator must not be equal to 0, else the function will be undefined. The next one is the trigonometric function. That's sine of x, cos of x, tan of x. In that case, x becomes the angle of the function. Another function we'll have is the exponential function, where x is the power of a particular number. So in this case, we are using a to represent any number, whereas e is a particular number in mathematics. I think 2 point something, I've forgotten. It's just like having pi, where pi is 3.142. So if we take 2 to the power x is equal to y, this is an exponential function because x is the power of 2. If we say y equal to 3 to the power x, it's also an exponential function. If we say y equal to 3.1 to the power x, all these things are exponential functions. Why? Because x is the power of the number. So that's what the exponential function is all about. Once x is the power, that function becomes an exponential function. Another function we have is the logarithmic function, log x, ln x. So both are similar, just that here we have base 10, whereas we have base e. That's this e we have here. If you punch your scientific calculator, you will know what the value of e is. So when we take log of x to base e, we'll call it lim. Whereas when we take it to base 10, we just call it log. Log x lim x. Then the last one I want to talk about is the hyperbolic functions. Sinh x, cos x, like that. So it's different from sin x and cos x. That's why they are called hyperbolic functions. Now, the next thing we want to talk about is the composition of functions. Take note, I didn't say function, I said functions because we need to have at least two functions to talk about composition. So, what's the composition of functions all about? The composition of two functions is a new function that is formed by applying one function to the output of another function. So when we apply one function to the output of another function, we call it the composition of functions. Take for instance, we have a function g of x is equal to 2x plus 1, and we have another function h of x is equal to x squared plus 2. So these are two functions and they are different. So we want to find f of x, which is equal to g of h. In other words, the composition of g and h, but in this case, g of h. Then we'll also be looking for f of x, which is equal to h of g. So let's look for the first one. F of x is equal to g of h. Now, what does this mean? This means that we should insert h where we have x in this function. Anywhere we find x in g of x, we'll put h there. So we have 2 into x squared plus 2 plus 1, which is equal to 2x squared plus 4 plus 1, which is equal to 2x squared plus 5. So this is g of h. What we did was we carried h of x, substitute x with it, then we got 2 into x squared plus 2, then plus 1. That gives us 2x squared plus 4 plus 1. That gives us 2x squared plus 5. Now let's find the next one. F of x equal to h of g. What do? We'll come to h, then carry g of x and put wherever we find x here. So that will be giving us 2x plus 1 squared plus 2. That will be giving us 2x plus 1, 2x plus 1 plus 2. And that will be giving us 2x times 2x, that's 4x squared. This will be giving us 2x, and this will be giving us 2x. So that will be 4x. Then this will be giving us 1, then plus 2. So this will be equal to 4x squared plus 4x plus 3. So you can see what composition of functions is all about. The last thing we'll be talking about is the inverse of functions. So what's the inverse of a function? The inverse of a function returns the original input when it takes the output of a function. So what this means is that if you make the output become the input value, then it will return the input value, that's the previous input value, as the output. So let's assume a function gave us 5 when x is equal to 2. Let's say we have y equal to 5 when x is equal to 2. What the inverse of a function does is that when you now make x equal to 5, that means your y will be 2. So the function that returns 2 when x is 5 is the inverse of the function that gives us 5 when x is equal to 2. Now let's find the inverse of the following functions. For the first one, we have f of x is equal to 3x minus 4. How do we know the inverse of this function? All we do is to say y is equal to 3x minus 4. Now, where you have x, you put y, and where you have y, you put x. In that case, x is equal to 3y minus 4. What do you do next? Make y the subject of the formula. You'll be having x plus 4 equal to 3y, y equal to x over 3 plus 4 over 3, or you say x plus 4 over 3. So this function is the inverse of this function. That means we say f inverse of x, take note of this, to the power negative 1. This is not power, it's just to show inverse. So f inverse of x is equal to x plus 4 over 3. Now let's try it. Let's say x is equal to 2. What do we have? F of x is equal to 3 into 2 minus 4. That gives us 6 minus 4. That gives us 2. So you can see that f of x gives us 2 when x is equal to 2. The same thing will happen here, that when we put 2 here, we should also get 2. Let's try it out. We have f inverse of x is equal to 2 plus 4 over 3. That's 6 over 3. That's 2. So when we put 2, which is y, we got 2, which is what? X, to show that these two functions are inverse of each other. Let's solve the next problem. For the next one, we have f of x is equal to 2x to the power 3. So what do we have? We say y equal to 2x to the power 3. Then where we have y, put x. And where we have x, we put y. 2y to the power 3. Make y your subject. X over 2 equal to y to the power 3. Then y is equal to cube root of x over 2. Now let's say x is equal to 2 here. We'll be having f of x equal to 2 into 2 to the power 3. This gives us 2 to the power 3 is 8 times 2, 16. So f of x is equal to 16. In other words, when x is equal to 2, y is equal to 16. Now, what do we do to confirm if this is actually the inverse of this function? When we put 16 as the input, we are supposed to get 2. Let's go ahead. Y is equal to cube root of 16 over 2. Y is equal to 2 divided 16, we have 8. Cube root of 8. That gives us 2. So it shows that this function is the inverse of this function. In other words, this function is the inverse of this function. So we've come to the end of the lesson. Thank you so much for watching. Please like, share, and do well to subscribe. Your subscription matters so much to me. Please do well to subscribe. You can also watch our previous videos. If you've not watched them, I can assure you that you'll not regret watching them. Once again, thank you so much.